All right, welcome back. CS3510, L17B. The topic is called FPTAS for Knapsack. What that means we'll say in a second. Sometimes we seek not simply a naive, stupid approximation algorithm, perhaps one that can be parameterized by an error that we want. So recall that we say an algorithm has an approximation algorithm has an approximation ratio based on how close its solution is to optimal. And we say that's the rho of n, and we call it a rho of n approximation algorithm. An approximation scheme takes as input additionally, besides what it was going to take on, an epsilon, and the epsilon will determine how much error it seeks, and is a 1 plus or minus epsilon approximation algorithm. So an approximation scheme is one which takes as input an extra number and allows you to say how accurate or how inaccurate you want it to be up to this factor. A polynomial time approximation scheme is polytime in n. For example, if you have a runtime of the form, let's say n cubed over epsilon, the runtime should always be a function of both n and 1 over epsilon, right? For any kind of approximation scheme. But we say the runtime of an approximation scheme is polynomial if it is polynomial in n. So this is polynomial in n, but not necessarily polynomial in epsilon. So for example, let's suppose you wanted 1% error. Oh, pop quiz. By the way, what is a 1 approximation scheme? Just from basic definitions, what is a 1 approximation scheme? It's perfect, yeah. The way we've defined this, one of these will always be greater than 1. The other is the reciprocal, so it must be less than 1, right? So 1 is always greater than 1. So a 1 approximation scheme basically means these are equal. So in some sense, the output is perfect. It's a perfect algorithm. Suppose I ask you for 1% error, right? No, let's say 10% error. What would the runtime be if we fix epsilon to be 10%? If our runtime was this specifically. Yeah, and that's pretty bad. So for such an algorithm with runtime, polynomial time approximation scheme, given a 10% error, you're still looking at a 10 to the 30 execution. Now what if I asked you for 1% error? That's really bad, right? So polynomial time approximation scheme, maybe not the best. Let's come up with another thing. Fully polynomial time approximation scheme is polytime in both n and 1 over epsilon. So for example, n cubed times 1 over epsilon squared, right? If I ask you for 10% error here, what is our quote-unquote runtime? But we fix the error. This is going to be O of if I ask for you for a 10% error, and we have a runtime of n cubed 1 over epsilon squared, what's our runtime? Yeah. Yeah. There's a constant there that may actually be important. But basically, you can wait twice as long and expect significant decrease in error in some sense. It's like the longer you're willing to wait, the more you can reduce your error. Notice though, at least as formulated, approximation schemes can never have 0 error, right? You cannot have 1 over 0. That's fine. But this is what we mean when we say an approximation scheme is polynomial time or fully polynomial time. A scheme that is fully polynomial time might as well be polynomial time for significantly small error. Right? This might as well just be a perfect algorithm if the error is small enough to tolerate. It's as if we were willing to tolerate if we're willing to tolerate multiplicative constants, we should be willing to tolerate 1% error in our solution. Right? That's all we're saying here. Okay. Pop quiz. What was the Knapsack? Everyone remember Knapsack? Let's go over it again. Right? Knapsack. You had a set of items, which was weights and values. And you seek to max the sum set S. So when you choose I in S, you max VI subject to the weight is below your threshold. Right? You choose some set of items to do so. And does anyone remember the Knapsack recurrence? In dynamic programming, it was dp of I comma j, where items 1 through j and current capacity of I. What was the Knapsack recurrence again? Yeah, take or don't take. So what was the first case? It was dp of
I minus 1.
I j minus 1. If wj exceeded I, right? Else it was the max of dp of I j minus 1 as if you could take the item, but you're just not going to because it's not worth it. Or dp of I minus wj, j minus 1 plus vj, right? If wj is less than or equal to I. Yeah, something like this, right? What was the runtime of this?
It was the weight times the number of items.
Yes. You've basically fill in that table. It's constant time. Pull some elements. The table's about that size. This is an exponential runtime, though, right? We agree. Why was this exponential?
Because the size of the input is not the same as the
Yeah, the input is approximately it's like log of w plus
log n.
yeah, for each of the each number is of that size, but you have n of them, right? So it's like n times log of v max plus n times log of w max, whatever.
Like 2 to the k.
Exactly, yeah. If you have n items, w takes log w bits to store. So if log w is equal to k, then this runtime is actually O of 2 to the k n. Exactly, yes. And we'll come back to like, why does that look polynomial but actually is exponential today in a second. I claim two things. First off, we can modify such a recurrence to have a different runtime. We could have a runtime of O of Vn, where V is the sum of Vi for all I. So the sum of all possible values, I claim we can have a runtime of Vn instead of Wn. Why is that true? Let's think about it for a second. What minor thing? V, big capital V, is the sum of all values. Why is it okay? What modifications need to be made to make that true? It may not be the case that's even better, right? It could be the sum of the values exceeds W. How about I leave it as an exercise? I'll just say I claim a minor modification to the dynamic programming recurrence we've given can give you a runtime of O of Vn instead of O of Wn, where V is the sum of values, right? Basically, you kind of do the same DP, but maybe instead of looking at prefixes of items, you can enumerate subsets of items. It's actually maybe a little not easy. It would take a couple minutes. Perhaps you believe me, though, that it can be done. It's not too bad. What we can do, the reason we're going to develop, as the title suggests, a FPTAS for Knapsack. And the way we're going to do so is basically by scaling down whatever that v is. This v here, we can severely underestimate the values of items, and if we do so, then this runtime becomes pretty simple. That's kind of what the idea is. What do we mean by scale down the values of items? Suppose we had v1 was like 11,283, and then we had v2 was like, let's say 11,287,000, and then we had like a 20 million, and then like a 1,1201, and then we had 20 million, like a 199, something like this. Okay, we had a bunch of values of items, right? And during the item selection, the value is needed to compute optimality of which one you're choosing, right? But why consider values of items up to such complexity? Let's just round everything down and then consider those rounded values. So here v1 prime would be just 11, v2 prime would be 20, and then v3 prime would be 20, right? Now certainly we lose some precision doing that. We lose something. But maybe if the items are so different anyway, we need not compare them digit by digit, bit by bit. If we can still choose a good enough set of items this way, maybe that's fine. And in fact, the parameter we will take in, epsilon, will tell us about how much rounding we want to do. Because that rounding will tell us how much we want to approximate by. That'll give us the final answer. So the core idea here is we basically just do naive knapsack, the same knapsack algorithm, but with adjusted weights instead, with rounded down weights to make comparison easier, rather than the actual weights. That's the core idea. Before we get into that, are there any questions? Okay. Here is our FPTAS algorithm. On input wi, and then let's say some epsilon. If any wi exceeds w, discard the item. Set v max to be the max item weight, item value. And then we are rescaling all the values. This v prime here is essentially a scaling down of the value vi, right? If you think about it, vi is smaller than v. V prime is smaller than v, right? So all we're going to do then is run the O of vn knapsack, and this actually should be the sum of the scaled down ones instead of the actual ones, with values of vi primed. Okay, we need to make several arguments now. First, we need to argue about correctness of the answer. We need to argue about runtime. We need to argue about optimality and so on. What is the runtime of such an algorithm? Well, this other stuff, this doesn't really matter. This is garbage, right? So just forget that. If we run the vn knapsack algorithm with scaled down weights, what can we say about this runtime? It technically runs an O of vn, right? But v is now not the sum of vi. V is not the sum of vi, but rather v is the sum of vi prime, right? And what do we know about vi prime? Sorry? Give me an overestimated vi. For all I, vi is less than or equal to what? I'll tell you, because we want the runtime in terms of n and epsilon. Let's just ignore everything except that n and epsilon, right? So we know vi prime is less than or equal to n over epsilon, right? So v is then equal to the sum of I equals 1 to n of vi prime, which is less than or equal to the sum of n, I equals 1 to n of n over epsilon, which means v is less than n squared over epsilon, right? So the runtime here then is going to be O of, what is that? N times n cubed over epsilon. Okay, so that is FPTAS runtime. That is fully polynomial in both n and epsilon. We need to argue the correctness. This is not an FPTAS until it's correct. So we know the runtime though. Are there any questions on the runtime? Do you agree with my estimate there? Okay. So now we need to argue about optimality. So suppose S star is output set of items. How off, and let's suppose C and C star are, for example, the values, the sum of values we wish, right? So we wish to seek not the underestimated values, because of course that's going to be different than the actual answer. But if we were to choose those items using the underestimates, the proxy items, the original set of items, how off would we be? So we are considering the sum of vi, not vi prime, but vi for I in S star. No, S. Yes. Wait. Sorry, I got it the other way around. Let's consider the optimal set of items that an ideal knapsack solution would produce, and let's consider the weights for the proxies that are scaled down, and we'll put that into something relative that we can compare C and C prime with, C and C star with, right? Well, we know something about vi prime, and is that it's equal to a floor function of values of vi, right? What's a way we can overestimate a floor function? Floors, ceilings, all are annoying.
Over epsilon Emax.
This is definitely more than that. That is definitely more than the floor, but we can underestimate that as well by a whole factor of n. Yes. Sorry, by a factor of 1 from each, right? Rounding down is greater than subtracting 1. So we can say that this is for I in S star of vi n over epsilon v max minus 1, right? Which is equal to the sum of vi I in S star times n over epsilon v max minus n. Sorry, this should exceed this, because we don't know how many items are chosen here, right? First off, do we agree with this? Okay? What is the sum of I and S star of vi? Problem-wise, what is that supposed to be? S star is the optimal set of items. Vi is the weights in the original problem. So if S star is the optimal set of items, and I'm asking you for the values in the optimal set of items, what should the sum of vi of S star be? It's the optimal solution, exactly. This is just, we'll call it C star n over epsilon v max minus n, okay? So just hold on to that for a second, but keep that there. We're going to use that to argue about the ratio between the optimal and the output. So the output C is equal to the sum of I in S, where S is the actual items of VI, right? And again, we don't actually return the proxy values. We use the proxy values to make simpler decisions, but we actually are going to return the original values, right? The ith item scaled down, we return the value of the ith item, not the scaled down value. So the output solution C is for S, the output of the algorithm. So let S be the, while C star and S star are the optimal, let C and S be just the output of this approximation algorithm, okay? And we know we can overestimate VI as a function of VI prime. So how can we get VI as a function of VI prime? Well, since VI prime is equal to the floor of VI n over epsilon V max, what do we know that VI must exceed? Let's do a shuffle. It's going to be VI epsilon max over n. Is that right? Okay. So we may overestimate each VI by exactly how we computed the proxy value. Oh. Thank you. Do we agree? Pull non-constant stuff out of there. Stuff that doesn't matter, let's move that out of the sum, right? What do we know about this sum, though? We computed previously that the sum of the proxy values is going to exceed here, whatever this happens to be, epsilon V max over n times C star n over epsilon V max minus n. Now, that's the sum not for the original, but that's the sum for the optimal solution. But that's okay because we know that if the optimal is, as we call it, optimal, then this solution has to be greater than or equal to it. So that's fine that we can perform this underestimate. Now, if I were to move stuff around, what should we get here? This is the second grade part. What's this? What should we do?
Get C star minus epsilon.
Almost. Okay, let's work through it. That cancels, C star. Minus. None of that cancels here, right? Except the ends. So we get minus epsilon V max. Double check me in that. Is that right? Okay, well, is it the case that we know that the value of the max should be less than the optimal? So in fact, we can even overestimate this by C star minus epsilon C star. So it is the case that if we bring that back down here, we get that C exceeds C star times 1 minus epsilon. So the ratio here is within a 1 approximation, is within a 1 minus epsilon approximation factor. I think I've messed up somewhere. should be the other way around. Maybe you take the reciprocal and you reparameterize instead of something else. I'm over it. It's fine. Either way, you're within a tolerable error. Before we mention, I'll just mention one more thing, kind of high level and not super detailed. Before, when we talked about this algorithm, there was many concerns that it was not exponential time. You see letters and you're like, that's polynomial, right? But the way that the exponential comes is not at all from n, or whatever letters that you're given. It's always a function of the size of the input. And because the input is exponentially smaller, that makes a runtime like this look bigger than it actually looks. So we say a runtime is pseudo-polynomial if the input in unary would make it polynomial. So if we gave the input in a worse way, it would be a polynomial runtime. What is unary? Have you heard of unary encoding before? Give me 25 in binary. What's 25 in binary?
1, 1, 0, 0, 1.
Is that right? I believe you. 25 in base 10 is what? Yeah? Okay, what is 25 in base 1? What?
Oh, 1, 1.
Yeah, so 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Yeah, okay. That's 25 in base 1, unary, right? So if the input to Knapsack were given in unary instead of binary, the input we would not have a log W plus n log V plus n log W, where these are VI, like whatever. I'll say max here. From that size, this is exponential size. This is an exponential algorithm. But instead, if we were to encode the input to Knapsack in unary, then we would have a size of W plus NV max plus NW max, right? And this runtime of O of Wn would not be exponential in the size of the input. It would just be polynomial in the size of the input, even though it's the same algorithm. So if we were to change the way we can give the input to something really bad, then the algorithm is polynomial time. The actual number of steps the algorithm takes does not change, but how we measure the algorithm does change. And an algorithm is said to be pseudo-polynomial if this is true, right? So the question is does NP completeness really even matter? We can give an FPTAS for Knapsack, right, up to an approximate factor that we care about. The polynomial is not too bad either, right? So the question is, does there exist an FPTAS for all of the other NP complete problems? When does there exist an FPTAS? And the answer is there exists an FPTAS for an NP complete problem if and only if its runtime is pseudo-polynomial. Knapsack and Knapsack-like problems are basically the only ones that we know that that's true for, right? Subset sum is another NP-complete problem that has a similar algorithm, and so on. But that's not true of, we don't think there is a vertex cover for, we don't think there's an FPTAS for vertex cover or anything else simply because we don't have pseudo-polynomial runtimes for them. The complexity of the exponential search for SAT or vertex cover does not come from the way you have to encode the input. It comes from a more innate kind of hardness. So Knapsack is kind of unique in the sense that there's an FPTAS for it, when that's not necessarily true for most of the other NP-complete problems. Right? Questions? Okay.